Hello everybody. Today I'm going to be talking about a question which on its face seems very simple, but in reality is not. That question is, what is electricity? I'm also going to be talking about where it comes from and how it works. How can we make it? What do we do with it? Because electricity is such an important thing in everybody's lives. We use it for absolutely everything. And a surprising number of people don't understand how it works. So in this video I'm going to explain in very simple terms exactly how electricity works, what it is, where it comes from, all of that kind of stuff. And the things I'm going to talk about in this video are universal. They apply to everything electrical, whether you're talking about the people who designed the computer that you're watching this on now, or the people who designed the power plants that will run entire countries, or people who make planes that can fly in the sky, or submarines that go in the sea. Everything that uses electricity will use these principles. They are completely universal. So I think it's important that everyone should understand them. The most basic question, what is electricity? At its most basic, electricity is just the flow of electrons from one point to another. They flow through a material, usually a wire in most cases, but it can be anything. I'll get onto that in a second. This here is a diagram of a copper atom. Copper is the most common metal that most wires and conductors are made out of because it's a very good conductor, but it's relatively cheap, easy available. It's a good all-rounder. They also use other things, so aluminium, gold, silver. Depending on the application, you use different metals. Every metal, most metals are reasonably good conductors, some better than others. Again, I'll get onto that in a second. Copper, we can see, is a very good conductor because each of these circles is what's called an electron shell around the nucleus of the atom, and each of those crosses is one electron. As you can see, copper has in its outermost shell only one electron, the rest of it is empty, which means it can very easily sort of pass that electron between the atoms. So when you have lots of copper atoms all around each other, these outer electrons can quite easily flow between the atoms, and they sort of move around like an ocean almost between all the atoms. That makes copper very good at conducting electricity because electricity is just the movement of those electrons. But why do the electrons move? And this is where it gets a little bit more complicated. Generally speaking, there's a lot more, but there are two main ways that we produce electricity: chemically and mechanically. Chemical electricity comes from things like this. This is a 9-volt battery. I'm sure everyone's familiar with these. These store energy chemically inside them and then release it as electricity when you need it. Mechanical electricity is more complicated than that. The way it works is you have a generator, we spin it round mechanically, and it will produce electricity. Mechanical electricity is a thing called AC. It's complicated and behaves weirdly. So I'm going to talk about that later, or if this video gets too long, I might cut it in half, and I'll have this video about what's called direct current, DC. That's the electricity that will come out of a battery like this. It's quite simple, fairly easy to understand. And then I might have another video, or the second half of this one, talking about AC, which is more complicated and does weird things sometimes. So, DC. At its base, there are these three units here. These are the most fundamental units of electrical science: the volt, the amp, and the watt. There are many, many other ones, things like ohm, farad, Henry. There are lots of other units, which again, I will probably make videos in future explaining all of them, talk about the various different components, what they do, how they work. I'm thinking I probably will do that. But for what we're talking about today, these three are the most important ones. These definitions look a bit weird. They talk about units you probably have never heard of before. But the SI definitions are 1 volt equals 1 joule per coulomb. 1 amp equals 1 coulomb per second, and 1 watt equals 1 joule per second. In reality, what that basically means is that when 1 amp of current flows through a conductor, there is 1 coulomb of charge passing per second. So when you have 1 amp flowing, if there's 1 volt of voltage across it as well, 1 joule per coulomb. So if 1 coulomb passes per second, that means 1 joule per second, and 1 joule per second is 1 watt. So if there's 1 volt, 1 amp, that will dissipate 1 watt in power. Watts are the sort of power that is used, amps are how much power is flowing, and volts are how hard it's being pushed. A good way to think about it would be a pipe. If you imagine the wire as a pipe with water flowing through it, the voltage is how much pressure pushes the water in the pipe. A very high voltage means there's lots of pressure and it'll push very hard. Low voltage means there's not very much. The amp current is how much water flows through the pipe. So is there lots of water or just a trickle? And the watt is how much power the water has when it comes out, so what we can do with it. We can then use this, so yeah, the watt is how much power we can get. So we can use this flow of electrons in order to do things. We can do work with them. We can make them turn a motor, or heat something up, or we can make them do maths, and we can make them show things on screens, and we can make them do all kinds of different things once we can control how they move. So I'm going to do a quick demonstration here. If I get my power supply like this, these leads here are set to pass 1 amp. And I have this here, which is a power resistor. It basically is going to dump all of the power. And what will happen is when I connect these leads to this and I turn it on, there is now 1 amp of current flowing through these wires. So if I take this point here, there is 1 coulomb of charge flowing per second through my fingers. It's coming through here, through this resistor and back again. This resistor is dissipating the power that flows through it as heat. It's converting the movement of the electrons into heat energy, so it's going to get hot when I run the current through it. It is currently dropping 0.29 volt across it, this resistor. So the pressure is 0.29 and the current is 1. Because volts times amps equals the power dissipation, that means that we have 0.29 watt, 0.29 joule per second being dissipated out of this resistor here, which will make it get warm. I can make that happen faster if I turn the current up. I'm now dissipating 3.2 watts of heat out this resistor, and it's getting really quite warm now, and I can't really hold it comfortably anymore, so I'm going to turn that off. But that is the basics of a circuit. Power flows through the wires, through a thing, and does something. What it does depends on what we want the circuit to do. We can make it do whatever we want. Now, I am going to go and get some stuff, and we're going to do a demonstration about direct current, how we can make current chemically, because that's a bit of a hard thing to get across. So I'm going to go get some stuff. This is a demonstration anyone can do, and I will show you how we can make current and then make it do work with just some random chemicals. So give me a second, I'll go grab the stuff. So what we're going to do here is we're going to replicate an experiment which is one of the first batteries, in fact the first battery ever made, approximately. We're going to replicate this experiment done by Mr. Volta, who has the volt named after him. He invented the battery basically. What he did was he took discs of zinc and discs of copper and layered them together with electrolytes in order to make a wet cell battery. What I have is I have some zinc plated nails here, I have some copper wires, and I have potato. The potato is going to act as the electrolyte. It's basically the wet paper. These are the zinc, these are the copper. What will happen is when we put them together, the zinc on these will oxidize and will have excess electrons, and the copper over here will take them. So the electrons will flow out of the zinc, and they will flow out through the circuit and to the copper. I only have one potato here, so I'm going to just cut it in half because I'm going to need to make 2 cells. But what we'll do is we will take the potato, we will stick in zinc, and we will stick in copper, and we'll do the same over here. We will stick in the copper and stick in the zinc. And if I then get this, which is a multimeter, I will set it to measure DC voltage, and hopefully 0.8 volts. See, we have voltage between these 2 points. It's not much. 0.8 volt is really not a lot. These are not good batteries, that's why we don't use them anymore. But see, again with this one, we have, if I move my hand so you can see the screen, 0.8 volt. So 0.8 per cell. I'm going to grab some other stuff, I'll connect these together, and I'll show you how we can use this to do work. So 1 second, I'm going to go grab some stuff. Quick interjection, I changed this, I added a 3rd cell in to increase the voltage a bit. So now, as you can see, the overall voltage that we're getting is 2.5 volt. It's not a very good connection on the top of this, but you see 2.5 volt as opposed to what we had before. So when I turned the lights off, you can see that we're getting a much more obvious light out of the LED. That's just because the voltage is a bit low. As I said, there's not enough pressure to push the electrons around that circuit, so adding a 3rd one will increase that pressure, push more. This is a battery, all of it is the battery, and each one of these 3 potato chunks is an individual cell in that battery. So one battery is multiple cells put together. So for example, these AA's are not batteries, they're cells. These are AA cells. When you put them together, lots of them all wired up, then that becomes a battery when you have more than one cell. That's a technical distinction, but worth pointing out. So, we have talked about what electricity is, one way we can generate it chemically, so direct current, how that works, how we can make that. One thing we haven't talked about yet is how it actually behaves in the circuit, how we can predict it and how we can control it to make it do what we want, which is the important thing as electrical engineers. Whatever we're doing, we need to make sure that it's in control and safe. That's to keep it safe. So, I'm going to talk about how we can control that, and there are a few things in here which I am going to say 99.9% of people are wrong about. It is just wrong. So, electricity will flow through the conductors in a circuit. You can have several ways of arranging things in a circuit. You can arrange them in series or parallel. So if we have a resistor, this is the symbol for a resistor, and I draw another resistor here, these 2 resistors are what we call in series with each other. That means that the current will flow through both of them at once in order to get through. I can also draw 2 resistors, but I can draw them like this. 2 resistors here, and we connect them like that. These resistors are what's known as in parallel, not in series. So current will flow through both of these to get to where it wants to go. So with the resistor here, the current will flow in here, it has to flow through both of them in line and then it'll come out. Whereas with this one here, it can come up here, go through here and come down, or it can go up, through and down. This is the first thing that almost everybody gets wrong. They will tell you that electricity will take the path of least resistance. That is just not true. Electricity will take every path available to it, and I mean every path. It's just that the amount of current that flows through each path is different, proportional to its resistance. People say that you get conductors and insulators, but again, that's not true, you don't. Absolutely everything will conduct electricity, with one exception. The only thing that does not conduct electricity is an absolute vacuum, which is the absence of matter. So everything else will conduct electricity. It's just some things are very, very bad at it, and some things are very good at it. So things that would be considered conductors are things like copper, aluminium, so on. They have very low resistance, current can easily go through them all. Things that people would call insulators are not insulators, they're just very bad conductors. So plastic, for example, the current can't go through it easily. It requires a lot of force in order to get through. Some current will always go through the plastic. It's not much. It's very, very minimal. I will demonstrate this now. I'm going to cut away to me with a piece of test equipment. I will prove to you that plastic conducts electricity. So 1 second while I go and set that up, because it needs me to set things up. What I have here, this device here is a specialist instrument. It's called an insulation resistance meter. These are expensive and honestly can be quite dangerous if you don't know how to use them. But I have one because of my work. I'm an electrician, so I'm a trainee electrician, but I have one of these meters. This is an old one, still works perfectly fine. The way that it works, this thing outputs 1000 volts onto these cables here, which I say it can be a little bit dangerous. I have over here, this is just an off-cut of cable, you see it doesn't go anywhere. I have connected one side of the high voltage to the inside cores. The other side I have just clipped onto the plastic. You can see there's a little bit of damage from where the teeth of the clip were, but it's just clipped onto the plastic. There's no exposed copper or anything, that's just dirt. There is no damage to the cable. So I will clip this on. I'll even clip it at a different place so you know I've not done anything to the cable. I'll clip this on, and then we'll have to zoom down on this display because it's going to be hard to see. But watch this needle very carefully, and you'll see it will move up and come. It will move up. It will bounce up and then come down again. That is from the capacitance of the cable charging up, which is not something I'm going to explain. But you'll see it will come up and it'll come down, but it won't quite go to zero. So you see, when I do this, I press the button, and you saw the needle move. The needle is now in line with 10,000 on the display. I don't know if you can see that. But that means that there is, because this is a 1000, so set to times 2, there is 20,000 million ohms of resistance between these two clips, which is a huge amount of resistance. That's an enormous amount. So when you compare that resistance of 20,000 million ohms to the resistance of the cable, which is like half an ohm, the enormous majority of that current will flow through the cable, but a little tiny part of it will flow through that resistance between the insulation, between the cores. Some of it will, but the vast majority of it will take the lower resistance paths. The setup I have here is to demonstrate a phenomenon known in the electrical industry as arcing, which is where the pressure is so high that the resistance of the air becomes low enough that they can actually overcome it and pass significant amounts of current through the air itself, through the gas. So even, as I said, everything is conductive, even gas is conductive. So I have these two cables here, they're connected to a power supply off screen, which will output a very high voltage. It outputs 11,000 volts. When I turn the power supply on, you will see that the electricity will jump between these two. It will jump through this gap here, between the two wires, through the air. It will use the air to conduct. So I will turn it on now, warning it will be quite loud. and we'll turn that off before I stink the place out with ozone. But as you could see, the electricity jumped through the air from one wire to the other. Even the air can be used as a conductor under the correct circumstances. I'm going to use this demonstration here to show that current will flow by all possible paths in a circuit and not just the shortest path or the path of least resistance, which is a common thing that I see people saying, and I'm going to now prove that they are all wrong. The path of least resistance thing is a massive oversimplification. As I showed, things like air and plastic and every single piece of matter will conduct electricity to some degree, usually not very well, but it will conduct some. So some current will always pass through them. It's just usually that there's such a small amount of current, it's not worth taking into account. So people say the path of least resistance as a way to simplify it. However, that's not true. This I will demonstrate here. I have wired this 60-watt bulb. Is in a bulb holder, and I have wired two wires in parallel on the live, which come out and go to here. One of the wires, as you can see, is short. The other wire is a much longer wire, and I have wired the neutral with a short wire. So what should happen if what people say is true and current will always take the shortest path, or the path of least resistance, all the current will flow through this wire, in here, through the bulb and back out here. And no current at all will flow in this wire, there'll be 0 amps. I will prove that wrong. I have my multimeter here, which I will turn on and I'll set to AC amps, which it will measure with the clamp here. I will then turn the light on, and I'll measure on the neutral, you should hopefully be able to see, 230 milliamps. I will then measure on this wire here, which is on the live, and if what they say is true, it should be 230, but it's not. See, we have 167. So, that means that there must be current flowing in this wire, and if I clamp my meter around that, put it here, as you can see, 67, 65 milliamps flowing through that wire. So there is in fact current flowing in both wires. Most of the current is taking the shortest path, but some current will also take the longer path, and the same thing will happen with every other resistance there is. So that 20,000 million ohm resistance between the cables, which I showed, some current, a very, very, very small current, but some current will flow through that. Some current will flow through the air, but again, it's very, very, very small amount of current. Some current will flow every single possible path, but the majority of the current will flow the least resistive path, which is in the cables. So we can control where the current will flow with the cables, even though it does take all paths. But sometimes we do have to be mindful of that. For example, in the high voltage, as I showed, it will conduct through the air. So we have to be mindful that it can conduct through the air, and we have to make sure to design things around that so that it doesn't, and it doesn't cause problems, and that the resistance is high enough that the current leakage through those paths is minimised to a point where it's not a problem. So as I just showed, current will flow all paths in a circuit. This is the theory, sort of the equations behind that. Back to series and parallel. Series resistors, you add the wires together. Parallel resistors, the current, or the total resistance, which determines the total current flow, is set by all of the resistances divided by 1 added together. So most of the time, if you had to say R1 is the cable resistance of 0.5 ohms, and R2 is the insulation resistance of, say, 20,000 million ohms, the R2 is so huge in comparison to R1 that people just say we can ignore it. And that's fine, you can ignore it because it is a negligible impact it will have, but it is there. These formulas, I'm going to go into more detail about them in another video, specifically about resistors and resistance, so I'm not going to do this. I have demonstrations to prove these too, but I'm not going to do those now. I'll do those in another video. But hopefully this video here has given you a pretty good understanding of how DC flows around in a circuit, how we generate it, and how it works. I will then make another video which will probably get posted the same day as this about AC2, which will talk about how we generate AC and some of the oddities that you get with AC in terms of how it can behave strangely in circuits, and some of the other things that it can do which DC cannot. So thank you very much for watching. If you have any questions, pop them in the comments. I'll do my best to answer them all for you. Remember to like, subscribe, and I will see you in the AC video, which I will put a link to somewhere, maybe tag in the corners somewhere, tag description, I don't know, I'll put a link somewhere. Anyway, thanks so much for watching, and I'll see you in the next one.